Here we are, week 12 of OChem, and 16 weeks last semester, so week 28 of OChem, and it's 420, 2020, man, dude, 420, 2020. Yeah, so today I was going to talk to you a little bit about this breast cancer drug called Tamoxifen. You may have heard of it. This is the molecule tamoxifen protonated, and it's a salt along with its citric acid conjugate base. So it's tamoxifen citrate. We'll talk a little bit about that, and then we'll finish up chapter 17, start chapter 18. So here's the protonated tamoxifen, and it must be the Z alkene for it to be biologically active, I believe. I don't know if it's less active the other way or not active, but you want the Z. And so let's say I cover up this side of the alkene. What's the higher priority, the ethyl or the benzene? The benzene's the higher priority. And then if I cover up the other side of the alkene, what's the higher priority, the lower benzene ring or the benzene ring with the oxygen and the rest? That one's the higher priority. So they both are on Z same side. So you can see this is the Z alkene. And tamoxifen, interestingly enough, it's been a drug that's been used to help women with breast cancer, but also some women who have a high genetic chance to get breast cancer can sometimes take tamoxifen like prophylactically before they have any signs of breast cancer, just in case they're worried about getting it. But I don't think it was approved in 2013, but I don't think it actually is used all that much because there are side effects. So do you want to start taking a drug before you have the cancer and have its side effects? I'm not sure. Some people do. And then it's a World Health Organization's list of essential medicines, the WHO, we hear a lot about nowadays. And it has a genetic price for it. And interestingly enough, in the poorer countries, in the developing world, it's like 7 cents to 23 cents a day for the drug, which is nice and cheap. But in the US, it's $1 per day. So I guess we can afford it. And then there's differences in prices too, I'm sure. And tamoxifen was originally made by a chemist named Dora Richardson. So Dora was exploring the drug field, and she was actually looking, and this happens a lot, she was looking for a different drug. She was looking for a drug, morning after pill, which is interesting. So Dora the Explorer was looking for the morning after pill, but she found an anti-cancer drug, or a cancer therapy drug, which is nice. And so instead of getting the morning after pill, Swiper came along and changed her results, but she said, "Swiper, no swiping." I don't know how the punchline works there, and it's probably not appropriate, but I think there's a punchline here. Dan's got to help me out with this one. But I remember Michaela used to like this when she was a girl. "Swiper, no swiping." Okay, so let's look at citric acid here. So it has 3 carboxylic acids on it, right? And an alcohol. Let's look at some pKa's. That middle carboxylic acid is actually the most acidic. That has a pKa of 3. It's lower than we would expect for like acetic acid's 5, right? We'll talk about why it's lower than 5. And then the next pKa can be either side because they're equivalent, right? If you look at it, it's symmetric. So the next one to get deprotonated, the pKa is 4.75. That's close to what you'd expect, right? And then the next one, whichever one is deprotonated first, then the other side can be deprotonated. Its pKa is 6.4. So it's a tricarboxylic acid. And why is the pKa one the lowest? Let's look at this guy. What makes this middle one different than the outside ones? Well, it has the alcohol right there. See that alcohol? How's that going to affect the pKa of this guy? Let's look. So OH, what kind of electron effects does it have? Is it electron donating or withdrawing? Now, a lot of you might be thinking right away, oh, that's a strong donor. Let's look at it in more detail for this example, though, because that alcohol is not on a benzene ring. It's on an sp3 carbon. So it's an sp3 carbon. So let's look at this in terms of electron withdrawing. It is, in terms of induction, it's electron withdrawing because oxygen's electronegative. In terms of resonance, it has no resonance because there's no p orbitals available for it to pi bond in. So unlike electrophilic aromatic substitution and some acid-base stuff we looked at, this particular molecule, you can't have resonance. So there's no resonance, so overall, it's an electron withdrawing group. So when you have an electron withdrawing group close to an acid, what does it do? It pulls electrons away from it, weakening that bond, making it more reactive and stronger, and hence it's the strongest acid. The alcohol is also associated with these other acids, but you can see it's further away, huh? Those ones, this one's right there. So that makes that's how I explain that being the strongest acid. When the conjugate base forms, its negative charge is stabilized by that electron withdrawing. Now, what about these two? Why is it that after the first one is deprotonated, why is the next one not as acidic? Well, if you think about it, after this one's deprotonated, it's a minus charge, and that one's deprotonated, it's a minus charge, or either one. Then when the third one needs to get deprotonated, it's got two negatively charged groups, and those are electron donating because they have extra electrons, right? So what do electron donating groups do to acids? They make them weaker. So it makes sense. And let's look at the mechanism for this one. So we have tamoxifen here, the Z alkene. It can reach out and deprotonate the most acidic carboxylic acid, and you get your citrate salt. And this is very common. A lot of drugs that we take and are in the medical field have amines that have that are protonated into the ammonium salts in their conjugate base. So this could be a citrate salt, it could be a sulfate, chloride. Chloride's real common. And when you do that, it's going to affect this molecule's, well, now it's a salt and usually a solid, so you can have it in a pill easily to prepare. And it's going to affect the molecule's solubilities, right? So we have a lot of nonpolar, but we have some polar here. So this will be more water soluble than the original, not amine. The ammonium is more water soluble. It's interesting, huh? And is this product favored? Let's see. pKa of that acid is 3. We saw on the last page. And our product acid is 9. So is this equilibrium favorable? Yeah, it's a million times as much product as reactants. And then here's one of the steps in the synthesis of tamoxifen, and it involves some reactions that we've been talking about, or similar to the ones we talk about. So if you look at this, you can see I've got this methoxybenzene, and this methoxybenzene is an ortho-para director, right? But more para, so I could see it up here. Oh yeah, it looks like it added para. And this guy's not an acid chloride, but we got this phosphorus pentachloride, huh? And then we got tin 4 chloride. It's interesting, right? So let's see if we can figure this out. What does this remind you of? So do you remember when you have an alcohol and you add PBr3, it produces the bromide, right? And this one we haven't been using it as much, but we did learn about this thionyl chloride. It'll turn alcohols into the chloride. Both go via an SN2 step in their mechanisms. And then you also remember when you have benzene and an acid chloride, you can do Friedel-Crafts alkylation. You can get a ketone like that. Now let's look at this. Does this seem reasonable that if you have your acid here and you add the phosphorus pentachloride, it might make the acid chloride? It does. So this acts similar to thionyl chloride. And actually, you know what? Thionyl chloride could also do this. It does the same thing. They must have had better yields with the phosphorus. And then if you add this, doesn't this look kind of like Friedel-Crafts, right? But instead of using aluminum chloride, you use the tin 4 chloride, and it goes para. So it's just kind of like the next generation reactions of the ones we're learning, the electrophilic aromatic substitutions. Pretty nice, right? And then this eventually goes through more steps and becomes the tamoxifen that you saw. Let's see. Let me go back a couple slides, see if it looks familiar to you. Yeah, do you see maybe how the methoxy, maybe that was the methoxy. We're actually going to learn about a reaction today that helps you produce Z alkenes. All right, so back to the schedule here. So we were kind of off schedule with the labs, but we're doing well. People are turning them in, keep them coming in, the ones that I got data for you and the ones you already have data for. And right now I'm going to be working on a lab exam, though. That's going to be this Wednesday, Thursday. So after I get that done, then I'm going to probably go over to lab and maybe do some of these fun ones, the green nitration. And then the green nitration I may do. I don't know. I'm going to decide. And but I'll get you that data for that stuff and some pictures and videos and things. But for the lab exam this week, go ahead and look at the lab exam guide. That'll step you through it. You kind of just go through that, and then you should be practicing those type of questions, and you'll do fine on the lab exam. The lab exam, I plan on giving it to you during your normal lab time. So if you're a Monday, Wednesday lab student, you can get that exam. I might give it to you. I'll give it to you before 2 p.m. earlier, but I'll give it to you on the Wednesday. If you decide, oh, you know what, with the COVID changes, I'm gonna just I have to work on that time now. What I normally would have had lab, can I take it Thursday? I'm fine with that. If you want to take it Thursday, just let me know. Send me an email. Somebody already did too, and I think I forget who it was. I think it might have been Sharon, maybe. Yeah, I'm pretty sure it was Sharon. Yeah, she's gonna take it Thursday. So anybody else though, just let me know. And okay, some review and a new one in this one here to start us, warm us up for today's lecture. So what happens with a ketone and a diol? I have an acid. It's not toxic acid, but it's an acid, and it's removing water. What are we gonna make? We're gonna make the ketal. It's an acetal, right? And then this one, I had 3 carbons in between the 2 alcohols, so there's 1, 2, 3 there. All right, what if I have, instead of a diol, I have just a single alcohol like methanol, and I'm using the toxic acid and removing water. Toluene is a co-solvent. We'll talk about how the toluene could help you remove water as an azeotrope later. So I got the ketone here, and it's gonna make the ketal again. And this one's not connected like the other one because it was a diol, but still a ketal. Both are excellent protecting groups. They're very stable in basic solutions. And then now we have this guy. You haven't seen a lot of this, but what is C6H5? That's a benzene ring. And normally benzene is C6H6, but it's one of the hydrogens replaced with a lithium. So that's the organolithium. Can add in, get deuterated, and that's just an old review, huh? No wiggle because it's not a stereocenter. We got that one, and now here's a new one. If you have a secondary amine, we're going to see this today, and you add an acid. This is triflic acid, one of the strongest known acids. You can get what's called an enamine. Did I put the name there? I didn't. But yeah, this is an enamine. We'll be doing that today. Back to our chapter outcomes, we learned about acetals, how to do the mechanism to put them on, take it off, and use them as protecting groups. They're great protecting groups against strong bases like sodium hydroxide, Grignards, organolithiums, alkyne anions, hydrides, etc. And next up, we're going to learn about imines. They're very similar to the acetals, but they involve nitrogen, not oxygen. And then even a step further from the acetal is an enamine. We'll learn about these. We make these with secondary amines, where the imines you'll see can be made with ammonia and primary amines. And then I got in our outcomes of Wolff-Kishner reduction, cyanohydride formation. I like these reactions, but I'm going to skip them this semester. I skipped them last year. And then also I'm going to skip the Baer-Villiger again too. It's a cool one. If you're interested, ask me. But we'll just, for this chapter, we're going to end it up with the imine, enamine, then the Wittig reaction. We're definitely going to do that one. And that's it for 17. We'll start chapter 18 at that point. All right, so today is the pajama day lecture. Just got out of the bath and in the pajamas. It's late already. What time is it? I always get to these late. 10:51 p.m. So if you're watching this lecture and it's like 3:30 tomorrow afternoon and you're still in your pajamas, you came right. You're good. So what do we got? We got a little review here. If I take this aldehyde, I treat it with ethanol, toxic acid, remove the water, it gives me the acetal. And now if instead of using an ethanol, I use this ethylamine, I get something new. This is called an imine. And it doesn't have two, like when you add an alcohol, you get 2 oxygens added to that carbon. For the imine, you just get 1 nitrogen. And you produce water in this mechanism, and if you remove it, then you drive the reaction towards product side too. And this reaction's very similar to the acetal papad-pede mechanism. We'll see, we'll go through this, and it'll actually make you better at that because it'll be the same kind of concepts we saw before. Because, like for example, we'll be under acidic conditions, so you expect to protonate first, positive charge organic intermediates, make bad leaving groups into good leaving groups, those things, right? So let's get started. I think I could do it all over here. Let's go with, so initially what do you think happens? An amine in Tamoxifen acid, it's going to definitely be protonated, right? So the amine gets protonated. I'll treat this as our true catalyst. Okay, so first step, protonation. We don't have to spell this out, but for fun, can do it. And then we got an ammonium, and the tosylate will be done with that. That'll just hang out for now. And then we have a aldehyde, which is a weak or a strong electrophile. The aldehyde's a weak electrophile. And the amine actually kind of a medium nucleophile. It's not totally weak, but it's not super strong. It's a medium one. But I like to draw this mechanism similar to the acetal one. So we're going to protonate and make our weak electrophile strong. To start. So we got two protonations again. It's looking pretty much the same as the acetal mechanism at this point. I'm going to wiggle this. This is like an E and Z protonated aldehyde. And now we have a strong electrophile and a medium, I'll call it, nucleophile. It's stronger than an alcohol, like ethanol as a nucleophile. And you can think of it as, well, nucleophiles are going to reach out their lone pair and add to things. And nitrogen is less electronegative than oxygen. So since nitrogen is less electronegative than oxygen, it's more willing to donate a pair of electrons to become a nucleophile. So let's do it. Add in here. So far, this is looking just like the acetal papad-pede mechanism, right? This black pen's kind of weak. Do I have a better one? I think I do. Yes. Okay, so that was an addition step. Papad. Oh, I almost forgot the hydrogen on the acetal. I mean the aldehyde. Okay, so I added that on, and you'll see overall to make my amine, I want to have the nitrogen attached to this carbon. And I don't want the oxygen anymore. But right now, I've got a good leaving group here, and a bad leaving group over here. Right? So I gotta switch that around. I don't want to have this guy leave, even though the reverse reaction does happen, but I want to pull it forward. So what am I going to do? I'm going to bring in a proton shuttle. Let's use the amine as the proton shuttle this time. Okay, and what's it going to do? It's going to deprotonate the ammonium. So it's looking still just like the acetal mechanism, papad, deprotonate. Go. And now they're both bad leaving groups. I want to get rid of the alcohol, so I'm going to protonate that and make it a good leaving group. Hopefully you've been practicing these mechanisms. After you practice them, you can get to the point where you can kind of see it in your head. And you don't have to, it's the best way to learn it. All right, so here we go, making that alcohol a good leaving group. Now that's a good leaving group. And what kind of situation we set up for here? We're set up for an elimination and a special one. So push-pull. Because this leaving group's ready to go and the nitrogen's going to push it off. And you can see we're going to get a double bond to the nitrogen. We saw a similar thing with the acetal mechanism, but there's going to be something different, you'll see. And now the water comes off, and that can be removed to drive the equilibrium towards the imine side. And so far it's been PAD, PE, looking the same, right? But there's going to be one thing that's different. When you got to this part where there was an oxygen involved, it no longer had a hydrogen on it to be deprotonated, whereas this does. So an amine can come along and deprotonate this. And then this is done. That last step was the deprotonation. And we have our imine. So it's due to the nitrogen being different than oxygen in its valence that you'll have a hydrogen at this point with a double bond, and it can stay on there. I wiggle this because this will be an E and Z imine. So like when the ethyl's on this side and the ethyl's on this side, that's the Z or the E imine. If that ethyl's over here on the same side as the other ethyl, it's the Z imine. So yeah, that's the mechanism for that one. Not too bad, huh? And you can reverse it too. This one spells out. Not that you need to know it, but it's just kind of something to do. PAD, PED, P-E-D. Yeah, it's a little shorter than the PAD, PED. Yeah. Yeah, so that's how you make imines. I want you to doyo the reverse. All right, let's do a little review and then I'll introduce the new one. So this should be easy now. This is an acetal with the diol, and water, which you remove, right? So we make, with the diol, we make the ketal, an acetal. With ammonia, you haven't seen this, but you should guess, I bet, if you try drawing it out, you'll see, you just get the imine without a carbon chain with a hydrogen on it. Same mechanism as we just did. So you get that kind of imine with ammonia. Now over here we've got an amine, but this one's not ammonia, it's a primary amine. Primary amine, just like the one we just did the mechanism for. So you should be able to draw that one up too. And you'll notice it's an amine again, an imine again. And I didn't wiggle this bond because it's symmetric around that 5-membered ring, so it's the same thing on either side. And now, what about this here? I went from ammonia to a primary amine. What kind of amine is this? This is a secondary amine. See how the nitrogen has 2 carbon chains on it, secondary. Nitrogen has 1 carbon group on it, primary. Okay, so what happens with a secondary amine? With a secondary amine, you don't get an imine. You get an inamine. instead of having a double bonded nitrogen, you have a single bonded nitrogen and an alkene over here. Sort of looks like an enol, if you remember, for the enol, like ketone to tautomerizations. Oh, I don't think I mentioned up front, like the first example I did was with an aldehyde. Ketone, as you see, reacts like an aldehyde. So now let's do the mechanism for this enamine. And you'll see, as we're getting better and better with mechanisms, it'll just kind of make sense. It'll be like similar to the pepad-ped and the pepad-ped. It might be pepad-ped, I forget. Let's draw it out and figure it out for ourselves. So initially, you have your secondary amine and your Citric acid, and they will react, of course. So let's do that. So we got a protonation step first. Citric acid's done. Then we take our ketone. Is that a strong or a weak electrophile? A weak electrophile. And it'll get protonated. The amine reformed, so that was another protonation. And our weak ketone electrophile is now a strong electrophile. And our amine is like a medium strength nucleophile. Not super strong, but not as weak as an alcohol. So it's more than willing now to add in. So it's looking the same as both the imine synthesis and the acetal synthesis at this point. But you'll see we'll get to a point, like we did before, that it'll have to change. Oh, no stereocenter on this one. I always get confused on these cyclic ones. Okay, now we're in the same situation again. Got a good leaving group and a bad leaving group. And what do we want to stay on? We want the nitrogen to stay on and the oxygen to come off. So we need to deprotonate that nitrogen. So our secondary amine is the proton shuttle. I'm going to deprotonate that ammonium. So this is looking just like before at this point. So you're probably thinking, oh, exactly the same. Been doing this over and over, and that's good because each time we work on this, we're getting better at this and also these. Oh, and then as a doyo, try drawing out all these mechanisms. We're doing this one now, but draw these ones out too, practice. And then I still have this oxygen, the alcohol is a bad leaving group, but I can make it a good leaving group. Alright, now our alcohol's ready to come off. Okay, and we are looking at another push-pull, right? It's going to be an elimination, a push-pull. The nitrogen is going to be pushing off the water, and the oxygen is going to pull its electrons towards it because it's got that plus charge it doesn't want. And then we look like we're in the same spot we were with the imine, but when we were doing the imine synthesis, we would, if we used ammonia, you'd have a hydrogen, 2 hydrogens in the plus charge, and you could just deprotonate one of them. For a primary amine, at this point, you would have an alkyl chain and 1 hydrogen with a plus charge. You could deprotonate. Can we deprotonate the nitrogen for a secondary amine? No, because it doesn't have a hydrogen, so you can't deprotonate it there. But what happens, interestingly enough, instead of adding to this, the nitrogen's different than the oxygen, it will deprotonate this alpha carbon. Imagine that's a ketone or aldehyde carbonyl, that's the alpha carbon. And what's going to be our base? Yep, you guessed it, the amine. Oh, and the water is removed. So the amine comes along, deprotonates that. I'll put a Roche hinge there. Oh, Roche hinge on 420-2020. And then deprotonate that, we get, that is a deprotonation, yeah. And that's it, we made our amine. So what did we spell out? Pad? Pad again. Oh, yeah, it's the same as the imine. Pad. Ped. And it all comes down to the, you get to this point, the nitrogen has no hydrogen on it, it can't be deprotonated. And you could see something maybe adding there, but for whatever reason, nitrogen's more. This is a thermodynamically controlled reaction. This is lower energy than if you add on another nitrogen. Now to end off chapter 17, we're going to talk about the Wittig reaction. The Wittig reactions, it's really nice. It's going to fill in a hole you probably didn't know we had. It's going to help us make Z alkenes. That's it. That wasn't something we could really do, making a Z alkene as a major product until now. So the Wittig reaction, it's kind of actually a sequence of reactions. So I'll show you. The first step is to take a bromide or an electrophile liquid Wittig group and do an SN2 reaction. And you do the SN2 reaction with triphenylphosphine. Triphenylphosphine is, I'm abbreviating it there. It's actually phosphorus with 3 benzene rings on it, phenyl rings. So it's a pretty bulky electrophile. But phosphorus is below nitrogen on the periodic table, so the atom itself, phosphorus is pretty big and its electrons are polarizable, so it winds up being a good nucleophile. Did I say electrophile? I meant nucleophile. So it's a pretty good nucleophile. It can do SN2. And you get initially what's called your Wittig salt, because this nucleophile isn't it's not, doesn't have a negative charge to begin with, so it's positively charged now, and it gets you this. So this is an SN2 to give us a Wittig salt. And cool chemists do pronounce the W like a V, so you say Wittig instead of Wittig. Okay, and then what we do is, this is kind of interesting. This hydrogen, this carbon, it's 2 hydrogens right here. Because the phosphorus has a plus charge, and also it's because it's believed phosphorus is d orbitals, it makes that carbon more acidic than a normal alkyl carbon. So it's got a little bit of an acidity to it, and you can deprotonate it with a strong base like N-butyl lithium. Now that is a super strong base, but you wouldn't normally still be thinking about deprotonating carbons. And so yes, you can deprotonate that and you get this guy. This is called an illid. So we're illin with the illid, or chillin with the illid today on 4/20/2020. And you can also draw resonance for this, but the resonance isn't that strong because the phosphorus doesn't even have p orbitals available for it. But I still draw the resonance because maybe I'm just lazy. I don't want to have to draw the formal charges. So this would be the resonance structure. And that doesn't break the octet rule for phosphorus because phosphorus is lower on the periodic table. It actually has to obey an 18 electron rule, so you can draw that. This is the illid. And also it has a plus charge and a minus charge. On adjacent atoms, that's what makes it an illid. When you have like a X and Y adjacent to each other with charges. But we also learned a term for a molecule like this. Is another one is called a Zwitter ion. Remember that? That's in your HPLC report. Zwitter ions are molecules that have positive and negative charges, but overall add up to no charge. And an illid is an example of a Zwitter ion. It's a Zwitter ion where the charges are adjacent. If the charges are not adjacent, it's not an illid, it's just a Zwitter ion. Okay, and then the next thing we do is we add either a ketone or an aldehyde to this. I'll add a ketone for this one. I'm going to add a ketone that's not symmetric so I can show you that I'm going to be making a Z alkene major. And this is how it works out. There it is, my Z alkene. So let's make sure, am I right about the Z alkene? If I cover this up, the tert butyl is the larger priority. If I cover up that side, the methyl beats out the hydrogen. Z same side, the Z alkene. And then you'll also produce a side product, a triphenylphosphine oxide. We're going to go over all the mechanisms. I'm hoping I don't even have to go over these first two steps, but this last one, of course, I'll go over that one with you. We'll see what's going on there. And yeah, so now we know how to make Z alkenes. So let's do that mechanism. The first one should be easy for you. It's just an SN2, right? And we make our Wittig salt. There we go. And then the next one, that should be easy too. It's just deprotonating. Make sure when you do this deprotonation, you deprotonate the correct carbon. It seems a little weird, but it's this one. Remember, directly attached to the phosphorus that you deprotonate. And if you want, we'll go right to that resonance structure. I can have a hinge there, swing it over, and show my illid. And of course you make the butane bastard gas. All right, and then I went to that one, but now now that I think about it, I want to draw the resonance for the having the carbon ion. I'll show you why. So I just did this resonance. It's kind of weird resonance on one arrow. But that's what it is. We got our illid. It's an illid because you have a negative and a positive charge on adjacent atoms. Okay, and now we're going to add in our ketone and see what happens. So I bet you can make a good guess at what happens in the very first step. What kind of reactivity do these ketones have? This whole chapter we've been saying weak electrophiles, right? That's one of its reactivities. And then what does this look like? Does it look like a nucleophile? Yep, it does. Carbanion there. It's actually a strong nucleophile. So what's it going to do? Add into the carbonyl. And when it does it in an interesting way. Actually, I think it has to do with, no, it's the next step that's interesting in terms of the stereochem. But I'll show you what happens here too. I'm gonna leave off the stereochemistry. I know it's something I never do, but it's kind of complex for this one, and I don't want to spend a lot of time on it. But this step's a bit tricky. I'm gonna number the carbons for us to make sure we're not messing up. So let's number these like 1, 2, 3, 4, and it's got the methyls off of those. 1, 2, 3, 4, those 2 methyls. And then we'll go like A, B, A, B. So we did make a bond between A and 2. We got the rest of those atoms there. And it turns out, it's interesting, phosphorus and oxygen love each other. I think I have something fun about that. Oh, I think I have a nice mechanism animation for this. Yeah, we'll do it. Yeah, I'll show it to you. Yeah, so phosphorus and oxygen love each other. They'll line up and they will actually go across and bond like that. So the classic Lewis base, Lewis acid, just form a bond right there. So you make a square intermediate, is what's believed. Like that. Then the intermediate is going to break down in a way to create our triphenylphosphine oxide. This is triphenylphosphine oxide, and our Z alkene. So it's simple enough. You'll see the phosphorus loves oxygen. Oxygen came over and bonded with phosphorus, and they love each other so much that they're going to continue to bond even more. So this bond is going to hinge on this carbon, swing down to make our alkene, and that's going to free up the oxygen to go make a double bond to phosphorus. And it turns out our alkene is most often the Z alkene. I'm not going to go into why it's the Z alkene, but that's why I also didn't show your stereochem here. It's a particular stereochem here that's actually, well, I could have shown it already. It's like, let's say this is dashed, or this is wedged, this methyl, then this methyl would be dashed. You don't have to draw this, I'm just explaining. This will be wedged, so you can see how they're going to end up on the same side. Now that we've added the VIDIG onto our alkene reactions, we are just alkene masters. We can do so much. But actually, before I do it, let me give you some quick review of these. If you want to do the VIDIG reaction, you have to first make your leading group on you got to make an electrophile that you'll react with the triphenylphosphine. So let's say I'm going to start with butane. If I add bromine and light, I can get my secondary bromide. Can secondary bromides do SN2 with a good nucleophile? Yes. So then I add my triphenylphosphine and diethyl ether, and this gives me my VIDIG salt. Simple E2 reaction. Okay, so after my triphenylphosphine has been added, I got the VIDIG salt. I can add the strong base like N-butyl lithium to make my ylide. And then when I add a ketone or aldehyde, I'll go ahead and add an aldehyde this time. My final product, the way you can visualize it, the easiest way, is to draw it up above it. It's similar to like the ozonolysis forward reaction, but this is it's different but similar. So let's do this, and I actually drew it the opposite of the major product, but I'll draw the major product, right? So what's going to happen is I'm going to get the E alkene, or the Z alkene like this, and then the triphenyl phosphine oxide. See how that works? I've got carbons 1, 2, 3, 4 here. 1, 2, 3, 4. A, B, C, A, B, C. And they're Z alkenes. So if I cover up the lower half of the alkene, the ethyl is the highest priority. If I cover up the top, the ethyl higher priority. On the Z same side, I get Z major. So let's actually do a retro of something like this. So if I give you a retrosynthesis and you notice that it's an alkene that is any type of Z alkene, it could be just trans, that's fine. But especially when it's a Z alkene, let's say this is the alkene. When you see something like that and you want to do a retro of it now, you can imagine, oh, I'm going to cut across here with the Wittig, and I can have that come from two different things. It can come from the ketone on that side and the ylide on this side. And just make sure you count your carbons right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. It's looking good. And then this can come from the Wittig salt, which comes from the bromide. All right, so that's one way to do it. Another way to do it is to have the ylide on the other side. And then instead of using a ketone, you have an aldehyde over here. Pretty cool, right? And you can see this coming from the Wittig salt, CpH3, and that coming from the bromide, and triphenylphosphine. Okay, so from now on, if you see a Z alkene, it should make you think Wittig. And this is going to fill in a big gap for us that we maybe didn't know we had about alkene synthesis. Let me show you some alkene synthesis, or retros, and a little bit of quick synthesis to show you what I mean. It's kind of cool. You guys have learned so much. You're going to see it right now. It's going to be like pretty amazing how far we've come. So let's do this. Let's say we have a unsubstituted alkene, just a ethylene, no substitution. What could that come from? It can come from the bromide in an E2 reaction, right? Or it could be a dehydration of the alcohol. Both of those will work. Okay, and then what about a monosubstituted alkene? Same thing, you can come from bromide, E2. It can be there, or the bromide can be on the end. Both of those work. And the alcohols will work as well, the dehydrations. Yep. And then what about a disubstituted alkene? Let's try like a geminal disubstituted alkene. That can come from the bromide, tertiary bromide, or, I'll write it below, or the primary bromide. That'll work too, right? No problem. And the alcohol as well. tertiary alcohol. Primary alcohol, both of those will work. And then what about, now let's keep going. Di-substituted, but let's do trans. And let's say we only want the trans disub. We don't want any cis mixed in there. Can we use the bromide? No, that's not the best. Remember on exam 2 you just did? This one will give you cis and trans. But if I want just the trans, I could use, so I don't want to use that one. If I want just the trans, I could start with the alcohol though, huh? Because the alcohol dehydration is under thermodynamic control, and it wants to produce the lowest energy alkene disub trans. So for instance, let me make sure you get this one. So if I have the bromide, and I treat this with would I want a big base or a little base? To go to the internal little base. It's going to give me both the cis and the trans mix. So I don't want that. I'd rather just the trans. If I start with my alcohol, I add some, say, phosphoric acid, heat minus water. I'm going to get the thermodynamically controlled lowest energy product. That'll be my major. Mechanistically, I know you might have not done this in a while, but I'm sure you could do it. There's an acid, so you protonate. Make it a good leaving group. It can leave to make a secondary carbocation, and then the dihydrophosphate can deprotonate. Or it could do E2 as well. E1 or E2 for the secondary. So now we know how to do unsubstituted, monosub, disubgeminal, disubtrans. What should I look at next? Disubcis. Oh, you know what? There's another way to do this too before I move on. This can also come from the alkyne, right? With the dissolving metal reduction, sodium metal in liquid ammonia and then water workup. And that's going to give away the next one. So if I wanted to make a disubcis, that you should hopefully say, oh yep, that has to come from the Lindlar's catalyst. Partial reduction of an alkyne. To get the cis, you won't get it major because it's higher in energy for the dehydration, and for the bromide you'll get the cis, but you'll get a mix. This one you'll just get the cis, so that's good, right? Okay, what about tri-substituted? That would be next. This can come from the bromide here. And that would need a bigger small base, or the bromide here, bigger small base again. So either of those will work. And the alcohols, this alcohol will work because to make that tri-substitute alkene is the lowest energy alkene from that alcohol. Would the other alcohol work? Yes, it will. That's good. Okay, so that was a tri-sub, but it wasn't E or Z because it has the two methyls that are the same on the sides. Let me look at one that's not a Z one, but an E one. Let's look at an E alkene. And an E alkene that happens to be lower in energy. So I'll make this like this, and I'll go. What about that guy? Can we do that one? We can do that one. So this is an E alkene, because if I cover up this side, highest priority is here. If I cover up that side, highest priority is here. The highest priorities are on the opposite sides. This is a E alkene. What could that come from? Let's try them out, see what works. Let's say I put the bromine here. If I put the bromine there, there's no hydrogen to deprotonate here, so it will go there, the alkene. But will I get just the E? No, I'll get the E and the Z, so that's not good. What if I put the bromine on the other position here? Now that one, if I use a big base, it'll choose the primary mostly, the methyl there. And if I choose a small base, it's going to actually pick over here mostly. It won't even give me the right regeochem. Not looking good. So the bromide's not the way to go with this guy. If I use an alcohol, let's see what that gives us. Let's say we put the alcohol right here. Could that work? I think it could work. You could, I can see this being protonated and get leaving, making a secondary carbocation, a hydride shift to make a tertiary, but you might have a little competition with the methyl shift. But if you make the tertiary carbocation there, this is the lowest energy tri-sub alkene. So I like that one. And I also like, I think, the other one. Let's try it. We're there. Oh, this one's not so good. Do you see a problem with this one? I want the alkene to go here to be tri-sub, but what might happen? Oh, you know what? This one's a problem as well. Shoot. Yeah, neither of these are that great because they're going to want to put the alkene here in the tetra-substituted area. Not great. I'm kind of stumped on this one. We'll have to come up with another way to do this one. I was trying to show you an example of E. I thought the E would be easier, but it didn't work out. That's okay. We're learning. But, okay, so maybe we can struggle with certain E alkenes. But what about the Z alkenes? No struggle now. Let me make one up here. We'll do that one. Okay, so this can come, could it come from the bromide or the alcohol? Let's check those first. I put my bromide here. Or here. What would happen if I use, oh, this isn't a steric, interesting. If I use a big base, I'll deprotonate there. A little base will be here, but it would give me both the E and the Z. So not that one. This one, if I use a small base, it can go there, but it'll give me E and Z, so that's not good. The alcohols, that alcohol, it's going to want to make this tri-substituted alkene, but it wants to make the E alkene. Because the E alkene will be lower in energy. And this one will be the same. So those don't work either, but we know how to do it from Vidig, huh? We could do it with the ketone on this side, or the with the your triphenylphosphine over here, your ylide. You can do it that way, or the opposite way. So yeah, the Vidig reaction is going to be very useful. Let's finish off chapter 17 with a nice retro here. Hopefully when you look at this one, you notice right away that that's a tri-substituted alkene, but more importantly, it's the Z alkene. Because if I cover up this side of the alkene, The phenyl is a higher priority than the methyl. Over here, that propyl is a higher priority than the hydrogen. So yeah, Z-alkene. So what does that make you think? Wittig. So in our retro, we'll start, first step back will be a Wittig. We could disconnect it two ways. We could have the aldehyde over here with the Wittig there. Or we can do the opposite. And let's look at both of them and see what we think is best. This lower one looks a little bit, oh, that's an H here. This lower one looks a little better to me because I could see putting the ketone on right away with the Friedel Craft. I could see this coming from the bromide. I know how to put a bromide on the end. The other one, I could see making that, and I could see putting the ketone on the benzene ring and then reducing to the alcohol, make it into the bromide. Actually, I don't know which is faster. They both look pretty good. I'm gonna go with this one. Let's go that illid, the illid here needs to come from the Wittig salt. And that needs to come from the bromide. And now that's a primary bromide. That's a bit of a tricky one, but we know how to do it. That can come from the alkene, the anti-Markovnikov hydrobromination, and then this can come from the secondary bromide, which can come from the alkane. The ketone here, this is acetophenone. It comes from benzene and the acid chloride. All right, we got a retro. Let's do our synthesis. I'll start with the illid first. So with my propane, I'm going to do a couple steps here. I'm going to brominate. It's going to go to the secondary carbon. Then I will add potassium T-butoxide for the E2, which will make the alkene I want. And then the alkene, I'll hydrobrominate, but anti-Markovnikov by adding the hydrogen peroxide. And then for this, I can start to do the new stuff. I'm going to add the triphenylphosphine. That's going to do an E2 reaction, give us the Wittig salt. And it's kind of weird, I know, but the phosphorus, the carbon that's directly attached to it, is a bit more acidic than normal. So you can add a strong base like N-butyllithium to make your illid. And then you can pause there. All right. Now just to finish off the reaction, the synthesis, we take our benzene, add our acid chloride, aluminum chloride to make the ketone. My pen's almost dead. And then finish off with our illid. And this will give us our desired alkene, not E, Z alkene. If you know, it'd be good for you guys to do, practice this one, but also do-yo this one. The rest of it. You can do it from that one too. Now on to chapter 18, enols and enolates. This chapter 18 is similar to 17. It's going to be ketones and aldehydes we focus on, but it'll be more of like the basic negative charged version. So in chapter 17, we had a lot of acid catalyzed reactions. And this chapter 18 is going to be more base catalyzed. So we'll start off with the acidity of aldehydes and ketones. We'll see why they're fairly acidic for carbons, and then move on down the line. Turns out aldehydes are fairly acidic for carbons. So let's look at the pKa of this guy. The pKa of this aldehyde is about 19, which is lower than you might expect because like an alkane, like butane, its pKa is super high, right? 50. So 19, why is it so low and where is it acidic? So is it acidic right here attached to the carbonyl? Seems like it would be because it's like, it's written out and everything, but that's not it. It's over here that it's acidic. Alpha to the carbonyl. And let's see why that's so acidic. If we add a base like a strong base, a common one to do this is lithium diisopropylamide, LDA, in say tetrahydrofuran, THF. So this one's a common one, and what can happen is you can see it deprotonates right here, making a lone pair on that alpha carbon, and a negative charge. And you should notice we have a lone pair, single bond, double bond, so there's resonance. And that's the key to why the pKa is pretty low. The conjugate base can be stabilized by resonance. I'll usually draw this resonance too as my major resonance. And I'm going to wiggle this methyl to show it can be cis or trans, E or Z. So this is, I think, the major resonance because the oxygen is more electronegative. It would rather the negative charge than the carbon. And they all have octets. It's not a case of not having the octets. And we would as well make the diisopropylamine in this reaction. So is this a product favored reaction? pKa of 19 for the aldehyde. The amine's pKa, what's that? It's not ammonium, it's just amine. Its pKa is 35. So the K equilibrium for this is very product favored. 10 to the 35 minus 19. 10 to the, it's late, 20 would be 15, 16, right? No. Oh my god, I'm so tired. Minus 19. 6 to 1. Yeah, 16. Oh, I was adding up the wrong thing. So 16 and 19 would be 15, 35. Yes, okay, good. So very product favored either way. So yeah, we can make these, what we call, this here is the enolate. We saw enols before in tetraomerizations, we'll see them again. And then when you deprotonate an enol, with this, you have this or an alpha carbon, it's an enolate. All right, let's look at a ketone. What do you think about the ketone? The ketone is actually not quite as acidic. It's pretty much the same, but the pKa for the ketone is more like 20. It's a little higher. So why do you think that is? It has alpha hydrogens, just like the aldehyde, that can be deprotonated, but over on the other side, I'm comparing just a hydrogen atom to an sp3 carbon. And how is an sp3 carbon related to a hydrogen atom? It's electron donating overall. So if you're electron donating, wouldn't that make your acid weaker? Pretty cool, right? Okay, so the next thing on our to-do list from chapter 18's outcomes is what? Draw the acidic and basic enol ketone tautomization. We could do that too. We've done it already though. I'll let you yo it. I'll just write it up. So for instance, if you took this and you added any base really, let's say sodium methoxide, it would be in equilibrium with its enol. And during this mechanism, you will make an enolate. It'll start off by deprotonating, negative charge organic intermediate. You know what, I'll draw it real quick. So, when your basic conditions, you have a strong base. So you can deprotonate, and I like to deprotonate and go right to my major resonance structure, putting the negative charge on the oxygen. Does this reaction seem product favored? Hopefully not, because pKa of the alcohol is around 16. The pKa of the ketone is around 20. So you say it's not all that product favored, which makes sense because we'd say the enol tautomerization lies heavily on the ketone side. And then the next step would be protonation of the enolate to make the enol. And regenerate your base, so the base is catalytic. Okay, and then you should be able to do the same one for the acidic conditions. So let's say I had, this lies heavily that way, yeah, heavily that way. I could do ethanol again if I want, and we can add Citric Acid. You should be able to draw up the mechanism for this. I guess with the Citric Acid, it changes the mechanism one step. You have to protonate the ethanol first, protonate the ketone, deprotonate. This would be a good doyo. See if you could do that one again. We did it in the past with the alkyne chapter 13. Okay, next on the list, racemization of alpha carbons. This one's a good one. So this is a problem chemists have often. You have an interesting molecule in which you need a certain stereochemistry for it to have its reactivity you want, like it might be a drug that needs a certain stereochemistry in order to work. But if you have some acid or base around, it can lose that stereochemistry. So let me give you an example. Let's say I have this ketone, and I really need to have that methyl there wedged out, so that stereo center is A, B, C, S. I need this to be S. If I get a little bit of, say, base around, say there's a little bit of sodium hydroxide and in the presence of this, it could give me problems. It could result in getting the RNS racemic mixture. So mechanistically, how could something like that happen? Hopefully you've already can see it. So if we're under basic conditions, means you have a strong base, it's going to deprotonate first. So it can deprotonate there. Row change, this goes here. I like to go right to my enolate. And at this point, that's when our stereochem is lost, that first step. See how there was a tetrahedral carbon here, now trigonoplanar. The stereochem was lost, and this is a reversible reaction. I'll draw it, I know it's reversed that way too, but I'll draw it coming this way. And when it reverses, the lone pair on the oxygen can drop down. You can hinge here on the alpha carbon and be protonated. And when it's protonated there, it can be protonated from this side of the board or the other side of the board. So the result is the hydrogen's added in a way, both sides, so you get racemization of the alpha carbon. Yeah, that's a term, racemization. It's made into a racemic mixture. It's racemized. Did I say acidic and basic? Why don't we do the acidic? Let's practice. Let's get good at this. We'll do another one. We'll do an aldehyde with some stereochem of the alpha carbon. Alright, let's see how this might happen. First off, your water will be protonated by the Citric Acid. Okay, and then our ketone, we need to remove that hydrogen and then put it back on. Do I want to deprotonate it right now and make a negatively charged organic intermediate? No, because we're under acidic conditions. So I want acidic. So I want a positive charged organic intermediates, right? So I'm going to go ahead and protonate the aldehyde first. So I can protonate this aldehyde, making it more reactive, and we know that that makes it into a stronger electrophile, but it also makes it more acidic. I'll show you. This is actually kind of similar to making the enamine mechanism. It's very similar to the enamine mechanism. Not the enamine, enamine, not enamine, enamine, yep. Whew, a lot of big words today, huh? Okay, so I'll erase that, get some more room. Okay, so I'm almost there. What's going to happen next is now this hydrogen is more acidic because of the oxygen plus charge. So a water molecule can come by, deprotonate it, and I'm not going to get the enolate, that's a negatively charged intermediate that's under basic conditions, but I'm going to get instead the enol. So I had a tetrahedral stereocenter here, Now it's trigonal planar. It lost the stereochem. And it can now be protonated again. And when it gets reprotonated, it's going to be a racemic mixture at that center. It's going to get racemized. And we're almost done with our mechanism. We just need to deprotonate the aldehyde. So you can see when chemists have a molecule that has stereochemistry, alpha to a carbonyl, they kind of cringe. They're like, oh, gotta be careful. If I just get a little bit of catalytic acid or base in my molecule, it can get racemized like that. You have to be extra careful with it.